Hello, and welcome to Lifelong Learning with Fulvia. Today's lecture is part 2 in our 3-part lecture series on black holes' gravitational monsters. After doing all the groundwork and setting the stage in our first lecture, today we finally get to black holes. We start with stellar black holes and attempt to answer the question, what is a black hole? Once we've established what they are, we'll see how we go about finding one. Then we'll talk about the 3 defining properties of black holes. And finally, we'll see what would happen if we were to fall into a black hole. With the last few slides, we'll talk about gravitational waves. The first gravitational waves were detected from the merger of 2 stellar black holes into one more massive black hole. We'll also see the merger of 2 neutron stars merging to form a black hole, the merger of a black hole with an unknown object, and finally the very recently announced merger of a black hole and a neutron star. Let's briefly review part 1. According to Newton, gravity is an attractive force between masses. It is a universal force, so every particle of matter exerts a gravitational attraction on every other particle. The gravitational attraction is proportional to mass. The greater the mass, the stronger the force. Now, unfortunately, Newton does not give us a cause for this force. Our most complete and current theory of gravity is Einstein's general theory of relativity. Einstein gave us an entirely new way of understanding space, time, and gravity. According to this theory, gravity is a manifestation of the curvature of space, and the space-time curvature is determined by the content of space-time, or by the mass and energy density at that point in space. The greater the density of the body, the greater the curvature, and therefore the greater the gravitational effect. So gravity is not really a force, at least not in the usual sense, but it is a warping of space-time, and what we perceive as gravity is just objects moving according to the geometry of space. Even though these are 2 different descriptions of gravity, we can see that in both theories, the greater the mass, the greater its influence, and that is the key. A gravitational field can be defined as a region of space surrounding a massive body which influences the motion and behavior of another body. We also talked about gravitational collapse. In a gravitational collapse, matter collapses in on itself under the effect of its own gravity. In various stages of a star's life, the inward gravitational collapse is balanced by some type of outward pressure, so that the star or the stellar remnant achieves hydrostatic equilibrium. In main sequence stars, the outward pressure is provided by the heat generated by nuclear fusion reactions in the core. When stars run out of their nuclear fuel, they will collapse into very dense objects supported by quantum-type pressures. An average star, such as our Sun, will collapse into a very dense white dwarf that is held up by electron degeneracy pressure. More massive stars will collapse to even denser objects known as neutron stars, which are held up by neutron degeneracy pressure and the strong nuclear force between the extremely tightly packed neutrons. Okay, so let's start part 2 by going back to our definition of a black hole from the first lecture. A black hole is a region of space where matter is compressed to such high density and the gravitational field is so strong that nothing can escape, not even light. We've talked about how in the final stages of their lives, stars collapse to compress matter to very high densities. And we've talked about gravity and the gravitational field. The greater the density of an object, the greater the curvature of space, and therefore the stronger the gravitational field. Now let's see what we mean by nothing can escape, not even light. To understand that, we need to understand the concept of escape velocity. Escape velocity is the minimum speed required to escape the gravitational influence of a massive body. And here it is in equation format. From this, we see that the escape velocity depends on the mass m of the body from which you are trying to escape. For Earth, it's 25,000 miles per hour. So if you launch a body with a velocity greater than 25,000 miles per hour, it will escape the gravitational influence of Earth and not come back down. If you launch a body with less than the escape velocity, it will not be able to escape, but will fall back down following a parabolic path. So the greater the mass, the greater the escape velocity. The mass of the Sun, this image is not to scale, so the mass of the Sun is 300,000 times the mass of the Earth, and its escape velocity is 1.4 million miles per hour. Now, from the equation, we also see that the escape velocity also depends on the size of the body, or the radius r of the body. Specifically, the smaller the radius for the same mass, the greater the escape velocity. If we could squeeze the Sun to the size of the Earth, its escape velocity would be 14 million miles per hour. If we could squeeze it to the size of a neutron star, its escape velocity would be 380 million miles per hour. That's about half the speed of light. So escape velocity depends on the density of the body. We will see that a black hole is a body of extreme density, and its escape velocity is greater than the speed of light. That's why nothing can escape, not even light. Okay, we finally have enough background information to actually talk about black holes. The concept of what we now call black holes goes back more than 200 years to the late 1700s. In 1783, the English clergyman and accomplished scientist John Michell proposed that some stars might have gravity so strong that not even light could escape. He called these hypothetical stars dark stars. He wondered what would happen if a star's gravity were so strong that the escape velocity were greater than the speed of light. Now let's recall that during this time, Newtonian physics was king. Besides his universal law of gravitation and his 3 laws of motion, Newton described the corpuscular or the particle nature of light. So Michell reasoned that if light particles were affected by gravity in the same manner as other kinds of particles, and if a star's escape velocity were greater than the speed of light, the light particles would be slowed down by gravity and eventually fall back down to the surface so that light would never be able to reach us, making the star invisible to an observer. Now, the flaw in Michell's reasoning is that today we know that the speed of light is constant, and that particles of light cannot be treated as other particles of matter and are therefore not slowed down by gravity. In 1796, the French scientist and mathematician Pierre-Simon Laplace, apparently unaware of Michell's work, postulated the existence of non-luminous bodies on the basis of his work on escape velocity and massive bodies. And his work was flawed for the same reasons as Michell's. By 1799, with the description of the wave nature of light, Laplace had deleted any reference to dark stars in his writings because it seemed unlikely that gravity could slow down a wave. Now, although flawed by today's laws of physics, dark stars can be considered the 18th century version of black holes. For the true concept of black holes to fully emerge, we would need a new theory of gravity. Of course, that new theory of gravity is Einstein's general theory of relativity. We've already mentioned that gravity is the manifestation of the curvature of space. Mass and energy curve space-time, and bodies will move according to that curvature. Now let's look at the gravitational effect on light. The first effect is the bending of light. As we saw in the first lecture, light bends as it follows the curvature of space. This was the first observational proof of Einstein's theory. The second effect is gravitational redshift. As light travels out of a gravitational well, it loses energy, which corresponds to an increase in wavelength known as redshift. Now recall that both Mitchell and Laplace thought that as light left a very massive star, it would slow down enough that it would eventually stop and come back down. But now we know that the speed of light is a constant, so it cannot slow down. So the decrease in the energy of light is manifested by a decrease in its frequency. Now, frequency and wavelength are related by this equation, where c is the speed of light, f is the frequency, and lambda is the wavelength. From this we see that frequency and wavelength are inversely related. If frequency decreases, then wavelength increases. Visually, we can see it here. As the frequency of the peaks decreases, the distance between each peak, or the wavelength, increases. The increase in wavelength is seen as a shift of light towards red, or the lower energy end of the spectrum. The important thing to remember is that the stronger the gravitational field, the greater the redshift of light. With general relativity, physicists now had a good enough understanding of both gravity and light to postulate the existence of black holes. So Einstein's equations would eventually reveal the existence of black holes, but it was not Einstein who predicted their existence. In fact, till the day he died, Einstein did not believe black holes would exist in nature. A true concept of black holes began to emerge in 1916. Karl Schwarzschild was a distinguished German astrophysicist. While serving in the German army in World War I, he found time to not only read Einstein's 1915 paper on general relativity, but he also set out to apply the new theory of gravity to stars. The Einstein field equations are very complicated. So, as any good physicist would do, Schwarzschild made some simplifying assumptions. He applied the equations to a spherical non-spinning star and calculated the first exact solution to the equations. Einstein was very impressed and submitted Schwarzschild's paper for publication. Now, although Einstein was impressed, he found one aspect of the solution very disturbing. Schwarzschild found that if you squeeze the mass of the star to a small enough radius, or a critical circumference, it would undergo a catastrophic gravitational collapse from which nothing could escape. At the critical circumference, light from a star would undergo an infinite gravitational redshift. Thus, in a sense, light would cease to exist. So we would not be able to see anything beyond the critical circumference. Now, Schwarzschild had two notable features. The first was that gravity collapses the object to a state of infinite mass density called a singularity. The second was the prediction of a gravitational boundary that would forever trap what was inside. The Schwarzschild singularity would more than a half a century later be called a black hole. Now, few people at the time were willing to take seriously the extreme predictions of highly compact stars. As mentioned, Einstein was very impressed with Schwarzschild's solution, but thought of them as a mathematical curiosity, not an actual physical reality. The Schwarzschild geometry predicted that for each star there is a critical circumference which depends on the mass of the star. The radius of the critical circumference is called the Schwarzschild Radius and is given by this equation, where g is the gravitational constant and c is the speed of light. The only variable in this equation is m, or the mass of the body. Now we can actually calculate the Schwarzschild radius for any mass. So for example, if we could squeeze the Earth to its critical circumference, We can't actually do this. But if we could, its radius would be less than an inch. That's about the size of a marble. If we could squeeze the sun to its critical circumference, its radius would be about 1.8 miles, or the sun would only be about 3.6 miles across. But just because we can calculate the Schwarzschild radius for any mass doesn't mean that any mass can gravitationally collapse to its critical circumference. Today we know that a star must reach a certain mass before it can collapse beyond its Schwarzschild radius. But at the time, no one believed that it was possible. In 1930, Chandrasekhar calculated the limit beyond which a white dwarf would not be able to resist a gravitational collapse. That limit is 1.4 solar masses. So if the remnant of a star's mass was about 1.4 solar masses, what would happen? Would it collapse to a Schwarzschild singularity? But those were not the words that Chandra used. He simply concluded his presentation by saying, "A star of large mass cannot pass into the white dwarf stage, and one is left with speculating on other possibilities." At the time, most physicists and astronomers took the other possibilities to mean a Schwarzschild singularity, but no one was ready to accept them as reality. So would a stellar remnant beyond 1.4 solar masses collapse to a Schwarzschild singularity, or would something stop it from happening along the way? Robert Oppenheimer would be the one to answer that question. In the 1930s, the concept of a neutron star was beginning to surface. Oppenheimer and his students calculated that stellar remnants beyond 1.4 solar masses would continue to gravitationally implode to become stable neutron stars. But just as Chandra had calculated the mass limit of a white dwarf, Oppenheimer found that neutron stars also have a mass limit. At the time, he calculated that the maximum mass a neutron star could have before a complete gravitational collapse was 2.6 solar masses. Today's observations put that limit at 2.16 solar masses. Beyond that mass, the star would collapse to form a Schwarzschild singularity. This was a key discovery. It meant that Schwarzschild's solution was not just a mathematical curiosity, but that these strange and exotic objects might really exist in nature. Nevertheless, these objects remained a mathematical curiosity until the early 1960s. Today we know that stellar black holes do exist, and as Oppenheimer had discovered, they are the evolutionary endpoint of very massive stars. The fate of a star depends on its birth mass. Stars with an initial mass of 0.1 to 8 solar masses, similar to our Sun, will collapse into a very dense stellar remnant which we know as a white dwarf. Any further gravitational collapse is held up by electron degeneracy pressure. In stars with a birth mass between 10 and 25 solar masses, gravity is just too much for the electrons. They eventually give up, and the core collapses into an even denser remnant called a neutron star. Any further gravitational collapse of a neutron star is balanced by neutron degeneracy pressure and by the strong nuclear force. And finally, in stars with a birth mass greater than 25 solar masses, gravity finally wins. Nothing can hold back the gravitational collapse, and the star will implode into a black hole. These stars are so massive that nothing can resist the gravitational collapse, and matter continues to implode into a mathematical point known as a singularity. A singularity is a point of zero volume, but with infinite density. If this doesn't make much sense to you, it's okay. You're in pretty good company, because all currently known laws of physics break down in a singularity. So what is a singularity? Generally speaking, a singularity is a mathematical term for a point at which a function tends to infinity. There are different types of singularities, but we are interested in gravitational singularities. So a gravitational singularity is a location or a point in space where the density and gravitational field or the curvature of spacetime is predicted by general relativity to become infinite. In other words, the curvature of spacetime becomes infinitely large, and spacetime as we know it ceases to exist. The first singularity we encountered was the Schwarzschild singularity as a solution to Einstein's field equations of general relativity. Schwarzschild's solution was saying that in a highly compact star, gravity would collapse matter to a central point of infinite mass density. Now, both Einstein and Eddington, the expert on stellar evolution at the time, were not happy with this aspect of the solution. They both felt that it made no sense for a physical object to have zero size and infinite mass density. Einstein's general relativity had somehow created a monster in which no one wanted to believe. Now, although general relativity predicts the existence and formation of a gravitational singularity, our current laws of physics break down at the singularity itself. The subject of singularities remained a mathematical and esoteric curiosity until the 1960s. In the late 1950s, the American theoretical physicist John Archibald Wheeler, who spent most of the 1940s and early 50s working on the atomic bomb, then the hydrogen bomb, turned his interest to gravitation and general relativity. In fact, he is credited with making the study of gravity a legitimate mainstream subject. However, he initially rejected the idea of a singularity. Specifically, he opposed Oppenheimer's view that very massive stars would die by imploding into a singularity, causing the space-time curvature to become enormous inside the imploding star. Wheeler stated that this implosion does not give an acceptable answer. By 1960, however, Wheeler was converted from a skeptic of black holes to a believer and advocate. Although Wheeler was now fully convinced that the implosion of a massive star must produce a black hole, the final state of the imploding stellar matter continued to bother him. To Wheeler, it seemed clear that the laws of general relativity must fail at the hole's center and be replaced by new laws of quantum gravity. As we will see in the next lecture, the search for an all-encompassing law that merges general relativity and quantum mechanics is still ongoing today. In the mid-1960s, the British mathematician Roger Penrose revolutionized the mathematical tools used to analyze the properties of space-time. In 1965, he invented new mathematical methods to explore Einstein's theory, specifically relating to the implosion of stars, and proved that a black hole always hides a singularity. In other words, every black hole must have a singularity at its center, regardless of how the black hole formed. Roger Penrose was awarded the 2020 Nobel Prize in Physics for his contributions to our theoretical understanding of black holes. There are two essential ingredients for a black hole. One, as we just saw, is a singularity at its center, where all its mass is concentrated in a point. The other is a boundary surrounding the singularity called an event horizon. So although all the mass has collapsed into a singularity or into a point of zero volume, the black hole has a non-zero boundary called the event horizon. So the event horizon is a spherical boundary marking the limit of a black hole from which nothing can escape. This is not a solid surface. It is simply the distance from the singularity where the escape velocity is equal to the speed of light. Nothing prevents matter or radiation from passing through the event horizon and entering the black hole, but once inside, it would have to travel faster than the speed of light to get back out, so nothing can escape. The size of the event horizon depends on the mass of the black hole. The radius is called the Schwarzschild Radius. Recall that this is the critical circumference that Schwarzschild calculated back in 1916. The radius is given by this equation, where g is the gravitational constant and c is the speed of light. The only variable in this equation is m, or the mass of the black hole. We can see then that the greater the mass of the black hole, the larger the event horizon. The event horizon is also known as the point of no return. Anything that goes beyond the event horizon cannot escape the gravitational pull of the black hole, so it can never come back out. In other words, any information, be it matter or radiation, entering a black hole is lost forever. Now, we've used the term black hole quite a bit so far, but black holes didn't get their name until 1967. So what were these objects called before that? Beginning in the 1930s and through the early 1950s, they were somewhat incorrectly called Schwarzschild Singularities. The Schwarzschild Singularity actually refers to the critical circumference, what we now call the event horizon, and not the actual singularity as we understand it today. An imploding star continues to exist even after it passes through the Schwarzschild Singularity, or the critical circumference, so there remains the issue of what to call the final object created by the stellar implosion. Throughout the late 1950s and 60s, these objects were given different names in the East and the West. In the West, they were called collapsed stars, and in the East, mainly the Soviets, they were called frozen stars. But neither one of these two names were fully satisfactory and didn't give a full picture of the collapsed object and the boundary around it. The West then started to call them gravitationally completely collapsed objects. By the late 60s, John Wheeler was becoming more and more dissatisfied with the name, and it was becoming very cumbersome. As he put it, after you say gravitationally completely collapsed objects enough times, you start to look for something better. Although it is not decisively known who first used the term black hole, Wheeler was the one who firmly adopted and popularized it, and he is often given credit for coining the term. In any event, since Wheeler's use of the term in 1967, it has been enthusiastically used by physicists and the general public. Okay, so far we've said that a black hole is the evolutionary endpoint of a very massive star, the remains of which have collapsed into a singularity. We've talked about the event horizon as the boundary around the singularity beyond which nothing can escape. We've talked about the escape velocity of a black hole being greater than the speed of light. But what is a black hole itself? Well, a black hole is a region of space where the gravitational field is so strong that nothing can escape, not even light. If you come away with one thing, this is it. A black hole is a region of space where the gravitational field is so strong that nothing can escape, not even light. Now recall that, according to general relativity, gravity is a manifestation of the curvature of space. The curvature is produced by the presence of matter. As we see in this embedding diagram, the amount of curvature depends on the density of matter. A gravitational field, then, is the region of curved space generated by a massive body, which influences the motion and behavior of another body in that region. A black hole is so dense that it is gravity at its most extreme, therefore produces an extreme curvature of space. So let's take a look. This is an animation of the curvature of space due to regular stars and a black hole. In the beginning, we just see stars. There is also a black hole, but of course we can't see it. As the animation goes along, an embedding diagram will appear, and it will become very obvious where the black hole is. As you can see, the black hole causes an extreme curvature of space. And now it is much easier to visualize when we say that if anything goes into a black hole, nothing can escape or come back out. Now, another thing this diagram shows us is that even though space is extremely curved, it is so locally. As you can see, far away from the black hole, the fabric of space-time is not affected. As an example, if the sun were to suddenly collapse into a black hole, we know that it can't, but if it could, the Earth's orbit would not be affected. The Earth would not get gobbled up by the black hole, but it would simply continue to orbit the black hole just as if the sun were there. So there is no reason to be afraid of black holes. Just don't get too close. Now, what about light? What happens to light inside a black hole? We mentioned that the escape velocity of a black hole is greater than the speed of light, and therefore it cannot escape, which is true, but that somewhat conjures up a rather Newtonian view that light is trying to move away from the center of the black hole but can't escape. Now, general relativity tells us that in a gravitational field, light will undergo a gravitational redshift, and the stronger the gravitational field, the greater the redshift. At the event horizon, the wavelength of light becomes infinite and ceases to exist, at least for an outside observer. But light does not cease to exist inside the black hole. So what happens to light once it passes the event horizon? For that, we need to remember that light follows the curvature of space-time. We just saw in the previous animation that inside the event horizon, there is an extreme curvature of space. Once matter has collapsed within the event horizon, it continues to collapse all the way to zero volume, resulting in a singularity of infinite mass density and therefore infinite space-time curvature. So all possible paths of light point inward toward the singularity, so light can never get out. Essentially, light gets trapped inside a black hole. Let's try to make a little more sense of this with a space-time diagram and light cones. We start with our space-time diagram with collapsing matter. As matter collapses in time, it will pass within the event horizon, then continue to collapse to a singularity. Now let's look at light cones. A light cone is the path that a flash of light emanating from a single event would take through space-time. Here is our event. The light from the event propagates outward at the speed of light. The sides of the cone represent the speed of light. We can only see that event if we are within the spreading cone of light. If we are outside the cone, light would have to travel faster than the speed of light to reach us. Now, to be more exact, a light cone actually represents both a future light cone and a past light cone. But for simplicity, we will only talk about the future light cone. Away from a black hole, the light cone is oriented as expected. Light from an event will propagate in all directions. As we get closer to the black hole, the light cones start to tip over to face the black hole, continuing to tip over more and more until it reaches the event horizon. At the event horizon itself, we see that one side of the cone is exactly on the event horizon, so light cannot escape. Within the event horizon, all the possible future paths of light point toward the singularity. So light gets trapped inside because it has no choice but to move inward toward the singularity. By the way, this is why it is called an event horizon, because any event that occurs inside is beyond the horizon. It cannot be seen by an outside observer. So we've just seen what happens to light inside the event horizon, but what about light just outside the event horizon? Outside the event horizon, there is a region called the Photon Sphere. This is a region of space where light is in a stable orbit around a black hole. Here is our black hole with its singularity in the center, surrounded by the event horizon, whose size is given by the Schwarzschild Radius. And here is the Photon Sphere. Gravity is so strong that light can travel in circles. It is sometimes called the last photon orbit or the last stable orbit, because this is the orbit for a photon traveling at the speed of light, and since nothing can travel faster than the speed of light, this is the final orbit. The size of the photon sphere is 1.5 times the Schwarzschild radius. Now, an interesting property of the photon sphere is that if you could stand at the photon sphere, of course you can't actually, but if you could, you would be able to see the back of your head. So let's see how that's possible. Here you are standing at the photon sphere and shining a flashlight directly in front of you. The light from the flashlight will travel around the black hole, reflect off the back of your head, and come back around and can be seen by your eyes. Therefore, you can see the back of your head. Now, up to now, everything we've said about black holes has been theoretical. Their existence is predicted by Einstein's general relativity, but Einstein was not the one to predict them. In fact, he did not think black holes would actually exist in nature. In 1939, he expressed his opposition to the existence of black holes in a published paper in which he stated, "The essential result of this investigation is a clear understanding as to why the Schwarzschild singularities do not exist in physical reality." In this case, Einstein was wrong. Theory tells us that a sufficiently compact object must implode and produce a black hole. In other words, theory tells us that black holes must exist. However, if we can't actually see them, how do we know they really exist? Although we can't see black holes directly, we can indirectly detect them through their gravitational influence on other bodies. The first strong candidate for a black hole was observed in 1971 as one of two stars in a binary star system. So how do we detect a black hole in a binary star system? Well, here is a typical binary star system, a system of two stars that are gravitationally bound to each other and orbiting around their common center of mass. Here we see the two stars, each with their own orbital path and both orbiting around their common center of mass. Now, these star systems and their motions are very well understood. Sometimes a single star can be observed to be orbiting around a center of mass, but there is no other visible star. There seems to be an invisible mass in the system. The invisible star may be a black hole. So even though we can't see it, its mass produces a gravitational effect on the other star. Now, binary stars systems are difficult to directly detect, but they can be indirectly detected through spectroscopy. Here we see a spectrum of a star with its spectral lines. The way we detect the star's motion is through the Doppler shift of its spectral lines. As the star moves away from us, the stars will shift toward the red end of the spectrum. And as the star moves toward us, the lines will shift to the blue end. So let's take a look. Away from us, toward the red, toward us, toward the blue. Away from us and toward us. This back and forth shift is called a star's wobble. From the amount of shift, we can calculate the velocity of the star, and from that we can calculate the mass of the unseen companion. If the mass is greater than 3 solar masses, and yet we cannot see it, then it must be a black hole. Now, although this sounds good in theory, in practice it is difficult to get very accurate results. So we need some other clues. If a black hole is orbiting another star, it can steal material from that star. As the material falls toward the black hole, it will be accelerated to nearly the speed of light. As it falls, it will spiral around the black hole. Now, since material is moving at such high speeds, it is incredibly hot due to friction between colliding material as it streams toward the black hole. The temperature can be millions of degrees, and at those temperatures, the material gives off X-ray radiation. As the extremely fast and hot matter swirls down toward the black hole, it forms a disk of glowing material surrounding the black hole called an accretion disk. The glow is the X-ray radiation which can be detected. So, if we could find a wobbling star with an invisible companion that is generating X-rays, we could find a black hole. Cygnus X1 was the first strong candidate for a black hole. It is part of a binary star system, Cygnus X1 being the very compact X-ray source, and its companion a blue supergiant. This is a beautiful illustration of the accretion disk around the black hole formed by the infalling matter from the blue star. We will talk about the jets that are seemingly coming from the black hole in the next slide. Cygnus X1 was first detected in 1964, but it wasn't until the 1970s that the very bright flashes of X-rays were observed multiple times each second, signifying that it was a very compact object. In 1971, the blue supergiant was discovered. Although it was in the same general location, it was far too big to generate the observed amount of X-rays. Later in that same year, observations detected a spectroscopic wobble of the blue supergiant. From that wobble and orbital velocities, astronomers were able to calculate the mass of the unseen companion. The estimated mass was greater than 6 solar masses, far too massive for a neutron star, so it must be a black hole. By 1974, as the quality of observations continued to improve, it was becoming more and more evident that Cygnus X1 was a black hole. Today, it is pretty unanimously considered the first object to be accepted as a black hole. Now, in a recent study, the mass of Cygnus X1 has been calculated to be around 21 solar masses. Another evidence of black holes is the detection of streams of extremely high-speed jets of particles seemingly coming from the black hole. This is an animation of a black hole feeding on its companion. We will see that as the black hole rotates, it pulls material from the star. As the particles fall toward the black hole, they reach speeds of about 90% the speed of light. Most of the particles will fall into the black hole and be gone forever. But some of the particles will get ejected away along the axis of rotation of the black hole, forming jets of high-speed particles. So let's take a look. Now, although the jets seem to be coming from the black hole, they are not actually coming out of the black hole. It is very important to remember that the jets of particles form outside the event horizon. So they come from the immediate vicinity of the black hole, but they do not come out of the black hole itself. So far, our search methods have been indirect detection through the effects of a black hole's gravitational influence on another body, and we see these effects via electromagnetic radiation. Here is Cygnus X1 with its accretion disk, which radiates X-rays. The jets of high-speed charged particles are detected electromagnetically in radio waves. And finally, the wobble of this blue supergiant, from which we can calculate the mass of the black hole, is observed through its electromagnetic spectrum. We have very convincing evidence that Cygnus X1 is a black hole, but nevertheless, it is still indirect evidence. So the electromagnetic signature simply says, I must be a black hole. But do we have any direct evidence of their existence? And the answer now is finally yes. When very massive objects move at very high speeds, they produce ripples in the fabric of space-time. These ripples are called gravitational waves. We will talk more about gravitational waves in a few slides. Now, since gravitational waves are produced by the object itself, the gravitational wave signature says, I am a black hole. The detection of gravitational waves in 2015 marks the first direct observation of a black hole. Now that we know how black holes form and how to find them, let's take a look at their properties. As mysterious as black holes are, they are pretty simple as seen from the outside. Black holes can be characterized by three and only three defining properties. The first and most important property is its mass. The mass of a black hole determines the strength of its gravitational field. Remember, the greater the mass, the greater the curvature of space, and therefore the stronger the gravitational field. The mass also determines the size of its event horizon. Recall, the event horizon is the boundary around the black hole singularity beyond which nothing can escape. The radius of this boundary, called the Schwarzschild Radius, is proportional to the mass of the black hole. This means the greater the mass, the greater the size of the event horizon. The second property is spin, or in physics terms, angular momentum. In other words, this property tells us how fast the black hole is spinning. And the third property is electric charge. Because of the way black holes form, their electric charge is usually zero. So this makes black holes even simpler. Now, these properties are special because they are visible outside the event horizon. All other details of the collapse object are lost to the black hole itself. In other words, the final state of a black hole does not depend on what it was made of before the collapse. So black holes are completely described by just three properties: mass, spin, and charge. Apart from these three properties, all other information about their initial conditions, for example, the shape and type of matter, all of that information is lost inside the black hole. In other words, a black hole preserves no other details of the object that collapsed. Now, these two statements are summed up by another of Wheeler's clever phrases: black holes have no hair. So no matter how complicated the initial state, a gravitational collapse to a black hole removes all hair, leaving a simple final state. In other words, black holes with the same mass, spin, and charge look exactly the same. They are indistinguishable from one another. Another way of saying this is, once you've seen one black hole of the same mass, spin, and charge, you've seen them all. So I'd like to end this section with what would happen if you did not heed my earlier caution and got too close to a black hole. Let's look at what would happen if you were to fall feet first toward a stellar black hole. As you get closer and closer, the force of gravity grows stronger and stronger. Now, because your feet are closer to the black hole than your head, gravity pulls much, much harder on your feet than on your head. Now, this effect also occurs on Earth, but because the gravitational field of the Earth is relatively small, the effect is negligible. But As you approach the extreme gravitational field of a black hole, gravity can be millions of times stronger on your feet than on your head. This great difference in gravity between your feet and your head causes extreme tidal forces that stretch and squeeze your body until you are stretched into a noodle-like shape. This effect is informally known as spaghettification. Now, of course, your body could only withstand so much stretching before the tidal forces would eventually snap it and break it apart, stretching and snapping each subsequent piece. But the concept of spaghettification still gives us a good idea of what would happen. And so we come to gravitational waves. We've already mentioned that through gravitational waves, we can directly detect black holes. So what are gravitational waves, and why are they so important? Gravitational waves are ripples in the very fabric of space-time that travel at the speed of light. It is important to note that they do not travel through space like electromagnetic waves, but they are propagating ripples in the very fabric of space itself. They are produced by masses moving through space. Just like when you drop a pebble in water, the water wave ripples propagate outward. When a mass moves through space, ripples in the fabric of space itself propagate outward. Although any mass moving through space produces gravitational waves, it is a very small effect unless it is produced by extremely violent and energetic cosmic events. So gravitational waves from these events spread across the universe like ripples on a pond. Gravitational waves were predicted by Einstein in 1915. He waffled back and forth a few times on whether he thought they actually existed. In the end, he believed they did exist, but they would be too faint to ever be detected. Einstein claimed that two orbiting bodies would lose energy to the surrounding spacetime through the emission of gravitational waves, and that would cause the bodies to ultimately merge. As we will see, it took 100 years, but this is exactly how gravitational waves were finally detected. So what is the importance of detecting gravitational waves? Well, gravitational waves provide us with a new tool to study the universe. Almost everything we know about the universe and cosmic objects within it comes to us from electromagnetic radiation. Gravitational waves are completely unrelated to electromagnetic radiation, so they give us a whole new realm of observation. So how do we detect gravitational waves? The main detector is LIGO, or Laser Interferometer Gravitational Wave Observatory. It consists of two identical interferometers with 4-kilometer arms. One is located in Hanford, Washington, and the other is about 3,000 miles away in Livingston, Louisiana. The reason there are two and so widely apart is that the detectors are extremely sensitive and will pick up any tiny vibration. Having two identical interferometers allows researchers to ignore any vibrations that differ between the two locations and only look for identical signals that occur at the same time at both locations. In other words, detectors located far apart cannot feel the same local vibrations, but they will feel a gravitational wave at virtually the same time. The other operating detector is Virgo, located near Pisa, Italy. With 3 detectors located so far apart, detecting and localizing sources of gravitational waves is greatly improved. So how do interferometers work? Well, let's look at a basic interferometer. We have 2 perpendicular arms with a mirror on each end, a beam splitter at the intersection of the 2 arms, a laser, and a photodetector which is connected to recording instruments. Light from the laser is split by the beam splitter into 2 identical beams which reflect off the mirrors, then recombined and are sent to the photodetector. When light recombines, it produces an interference pattern, hence the term interferometer. If the arms are exactly the same length, then the two beams are designed to destructively interfere and cancel each other out. As gravitational waves propagate, they stretch and squeeze space itself and everything they pass through. So passing gravitational waves will change the length of the arms as they go by, stretching and contracting the arms. The effect is that the two light beams will travel different distances so that when they recombine, they will be out of phase and produce an interference pattern at the photodetector. Now, while this seems pretty simple in principle, the change in arm length due to a passing gravitational wave is 10,000 times smaller than the size of a proton. That's 1/1000th of a billionth of a meter, or 1/10000000th of a nanometer. And yet, LIGO and Virgo have the technology to detect this. So let's see how gravitational waves relate to black holes. We mentioned that the strongest gravitational waves are produced by cataclysmic cosmic events. Examples of some of these events are merging black holes, merging neutron stars, supernova explosions, and quite possibly from the Big Bang. Now this will show an animation of two orbiting black holes. Each black hole curves space, so we have two curvatures close together. Since the black holes are orbiting each other, the curvature of space is not static, producing waves that propagate outward while carrying away energy. So let's take a look. We can see that the waves are not traveling through space, but it is the disturbance of space itself that is propagating outward. In this animation, we will see two black holes continue to orbit each other until they merge. We will see that as the black holes orbit each other, they lose energy through the emission of gravitational waves, causing them to gradually spiral inward toward each other and gain speed as they get closer and closer until they finally merge to form a single, more massive black hole. In the final moment, the two black holes are orbiting at nearly half the speed of light, and when they finally merge, they convert a portion of the combined masses into energy, which is emitted in a final burst of gravitational waves. So let's watch the animation. Here we see the two black holes orbiting each other. Their orbits will spiral inward faster and faster until they merge, emitting a final burst of gravitational waves that propagate outward. The final burst is called a chirp. We will come back to the chirp in a few slides. Next is an actual computer simulation. It was created by solving Einstein's equation and using data from the LIGO Observatory. This simulation shows how the merger would appear to our eyes if we could get close enough. The extreme gravitational field of the two black holes warps space and time as they orbit each other, as we can see by the chaotic gravitational lensing effect of the stars behind the black holes. And as they continue to orbit faster and faster, they finally merge to form one larger black hole. Now, the detection of gravitational waves has ushered in an emerging brand of observational astronomy called gravitational wave astronomy, which collects data about objects such as neutron stars, black holes, and cataclysmic cosmic events. This is a collection for a wide range of compact objects. The blue objects are black holes detected with gravitational waves. In purple are black holes detected indirectly through electromagnetic radiation. In yellow are neutron stars detected electromagnetically. And in orange are neutron stars detected with gravitational waves. Now, to simplify all these dots, let's look at this event. This tells us that two black holes of approximately 18 and 24 solar masses merged to form a black hole of around 40 solar masses. These events are designated by the year, month, and day the gravitational wave was detected. We will look at 4 of these events and their significance in a bit more detail. The first is the first ever detection of a gravitational wave from the merger of 2 black holes. The second is the merger of 2 neutron stars. The third is the merger of a black hole with an unknown object. And the last is the merger of 2 black holes into an intermediate mass black hole. Our first event is the merger of 2 black holes. This is the first ever direct detection of gravitational waves 100 years after they were predicted by Einstein. Recall that although he predicted their existence, he never thought they would actually be detected. The primary and secondary black holes with masses of around 36 and 31 solar masses respectively merged to form a single black hole of around 63 solar masses. Although the detection was in September of 2015, it took a few months to confirm the data. In February 2016, the LIGO-Virgo teams made the historic announcement. And as expected, in 2017, the Nobel Prize in Physics was awarded for this discovery. Our next event is also of historic importance. This is the first cosmic event that was observed in both gravitational waves and light. The gravitational signal from the merger of the 2 neutron stars was detected by both the LIGO and the Virgo detectors. At nearly the same time, the Fermi Gamma Ray Space Telescope detected a gamma ray burst from the same area. The aftermath of the event was subsequently followed up by 70 ground and space-based observatory. This observation truly ushered in the era of multi-messenger astronomy, the ability to see and study the same cosmic event using multiple types of signals. This gives us a fuller picture of some of the most mysterious phenomena in the universe. Already, this observation has provided some answers to decades-long questions, such as where half of all the elements heavier than iron are produced, and it has confirmed Einstein's prediction that gravitational waves travel at the speed of light. The next event is the merger of a black hole with an unknown object. This event was observed by both LIGO detectors and by the Virgo detector. The primary mass is a 23 solar mass black hole, consistent with the regular population of stellar black holes. The secondary mass is an unknown 2.6 solar mass object. This object falls within a lower mass gap for dying stars between 2.5 solar masses and 5 solar masses. And this object falls right within that gap. So, is it the largest neutron star ever observed, or is it the smallest black hole? Well, we don't know yet. Another interesting aspect of this event is that no electromagnetic counterpart, or no light, was found. So the black hole may have eaten the neutron star in one gulp. Now, since then, the LIGO-Virgo collaboration has reported 2 other candidates within this mass gap, both resulting from the merger of 2 neutron stars. Our last event is another merger of 2 black holes. This merger was between 2 very large black holes and produced an even bigger one. This is the first direct observation of an intermediate mass black hole. That in and of itself is a great discovery, but the 85 solar mass primary black hole is also of great interest. Based on our current understanding of massive stars, it is thought that black holes with masses between 65 and 120 solar masses cannot form by a collapsing star. This is known as the upper mass gap. The 85 solar mass black hole falls right within this gap. So this tells us that very massive stars either can form high-mass black holes, or that these black holes may have formed by a previous merger of 2 smaller black holes. In any case, all of these events push our boundaries of knowledge. Just recently, the LIGO-Virgo collaboration announced the first ever detection of two separate black hole neutron star mergers, as we see highlighted here. The first was detected in January 5th of 2020, and the second was detected 10 days later. Not only is this the first detection of this type of merger, but it is the first evidence of a neutron star black hole binary system. Astronomers had been looking for decades for such a system. No electromagnetic signature has been detected in association with these events, so it is likely that the neutron stars were swallowed up whole by the black holes. Together with black hole mergers and neutron star mergers, the neutron star black hole mergers finally complete the family picture of compact object mergers. Now let's talk about the sound of two merging black holes. First of all, gravitational waves from merging black holes have a very distinct signal. As the two black holes spiral into each other, the frequency and amplitude of the waves increase. The frequency continues to increase until it finally ends with a chirp, when the two black holes merge and send out the final burst of gravitational waves. After that, everything comes to an abrupt stop. So how can we hear the chirp? The truth is, we cannot actually hear the gravitational waves from merging black holes. But we can convert gravitational wave frequencies to sound wave frequencies. It just so happens that the frequency range of the gravitational waves that LIGO and Virgo can detect is within the frequency of our audible range. So if we convert gravitational wave frequencies to sound frequencies, what we would hear at first is a low hum. Then as the black holes got closer and closer and orbiting faster and faster, the frequency would increase, and therefore the pitch rapidly increases and ends with a final chirp, indicating that the black holes have merged. So let's see if I can imitate that sound. Whoop. And one more time. Whoop. Now, from the frequency, amplitude, and duration of these events, scientists can determine properties such as mass, density, and rotation. In other words, gravitational waves carry the encoded history from the cosmic events that created them. This ends today's lecture. So far, we've talked about stellar black holes formed by the collapse of very massive stars at the end of their lives, and we very briefly mentioned intermediate mass black holes as forming from the merger of two stellar black holes. In the next lecture, we will talk about supermassive black holes, the true gravitational monsters that reside at the centers of most galaxies. We will see how the story of supermassive black holes starts with the discovery of quasars. We will talk about the first ever image of a black hole at the center of the M87 galaxy. Then we will briefly talk about other subjects related to black holes, such as Hawking radiation, black hole evaporation, and very briefly, quantum gravity. I hope you've enjoyed today's lecture, hope to see you next time, and thank you for watching.